last few classes we are studying about the continuous system. So, we have seen two different types of equations in this continuous system of one dimensional system. One is the wave equation, for which we have taken the systems of lateral vibration of taut string, then we have taken longitudinal vibration of rod and the torsional vibration of the shaft, and we have seen another type of equation, that is the Euler-Bernoulli equation, where you have a fourth order equation, and in case of wave equation you have a second order equation. So, in the previous classes we have studied about the Euler-Bernoulli beam with different boundary conditions such as simply supported boundary condition, clamped boundary condition, cantilever beam and free beam. Also we have studied about the longitudinal vibration of rod and the lateral vibration of taut string. So, already we have solved this wave equation and found the general solution for this wave equation, and applying to different boundary conditions we have studied the mode shapes of longitudinal vibration of rod and lateral vibration of taut string. So, today class I am going to tell about the mode shapes of the torsional vibration of rod. For example, I will show you the vibration of or mode shapes of a fixed rod and a rod with an attached mass and a rod with in which in the two ends you have the inertia. So, in these cases you can see that for this only for this fixed case you will have a very simple frequency equation, but with increase in this complexity of the system, that is when you are adding only one mass or when you are adding only two mass, the frequency equations are getting complicated and you cannot solve it by manually. So, you may have to go for the computational or you have to use the computer to find the solution for these systems. And in addition to this, I will tell you about these initial value problems, and also briefly I will tell you about this force vibration and by using this modal analysis method you can study the force vibration of a continuous system. So, to start with, so let us find the mode shape of this fixed rod. So, in case of the fixed rod, so already you have found the equation motion for this rod. So, in case of a rod, torsional vibration of a rod, the equation motion can be written in this form: del square phi by del t square equal to c square del square phi by del x square del square. So, here let me take theta, let del square theta by del t square equal to c square del square theta by del x square, where theta is the torsional displacement or the rotation of the shaft, and this rotation I will express in terms of as a function of, it will be, I will express this as a function of phi x and qt. So, here phi x is the mode shape of the system and qt is the time modulation of the system. So, already you have derived this equation by using Hamilton principle, and also you can derive this equation also by using this Newton's method. So, in case of Hamilton principle, you take the kinetic energy of the system and take the potential energy of the system. Potential energy is the strain energy stored due to the shearing effect of the shaft. By taking these things you can apply, you can find the Lagrangian of the system L equal to T minus U. By taking that Lagrangian, then you can apply the Hamilton principle to find the equation motion. So, the equation motion is in this form: del square phi by del t square equal to c square del square theta by del x square, where c square equal to g by rho. So, this is c square equal to g by rho, or c you can write equal to g by rho. So, where g is the rigidity modulus and rho is the inertia per unit length of this system. So, by taking this del square theta by del t square equal to c square d square theta by dx square, which is the wave equation, and this is the general solution for this case which we have already obtained. So, let us find this frequency equation for this case. So, from the general expression, you know this phi x can be written in this form. So, phi x equal to a cos omega by c x, a cos omega by c x plus b sin omega by c x. Here qt is the time modulation and it can be written in this form c1 cos omega t plus c2 sin omega t. So, by taking this time modulation c1 cos omega t plus c2 sin omega t and this general mode shape phi x equal to a cos omega by c x plus b sin omega by c x. So, now you can apply the boundary conditions in this case. So, in case of the fixed beam, or in this case of the fixed rod, so as both ends are fixed, so there will be no rotation in these fixed ends. So, as there is no rotation in this fixed end, that means theta 0 t equal to 0, and in this side theta L t equal to 0. So, theta 0 t equal to 0. So, this implies for all time this theta equal to 0. So, that means this phi 0 will be equal to 0, as we are substituting theta equal to phi x into qt. So, as for all the times this boundary condition or at this boundary rotation will be equal to 0. So, you can take phi 0 equal to 0. Similarly, here you can take phi L equal to 0. So, now substituting these two boundary conditions in this equation of mode shape. So, you can write, so phi x, so if I will write this phi x equal to, so by substituting x equal to 0, so cos 0 0, so you will have 0 equal to a plus, so sin 0 equal to 0, so b into 0. So, this means this a equal to 0. Similarly, now by putting this boundary condition phi L equal to 0, as already a equal to 0, you can write phi x equal to b sin omega by c x, already a equal to 0. So, by substituting a equal to 0 in this equation, so you can write phi x equal to b sin omega by c x. Now, substituting this phi L equal to, so phi L equal to 0, you can write b sin omega by c L equal to 0. So, this is equal to, so this implies already, as I told in the previous cases, this b sin omega c omega L by c equal to 0. So, b cannot be equal to 0, because when b equal to 0, this will lead to the trivial solution of the system. So, in this case of the rod, so this is the rod. So, in this case, so in this rod you are fixing at both the ends of the rod, and so when both ends are fixed, so at these ends there is no vibration at these ends. So, you have taken this phi or theta 0 equal to 0 and theta L equal to 0. So, the mode shape phi 0 equal to 0 and phi L equal to 0 you have taken. So, when you are taking b equal to 0, so the total expression phi x will be equal to 0. So, that will lead to the trivial state solution. That means there will be no vibration of this rod, or the rod will not rotate, but as we are considering the rotation of this rod, so we have to take b not equal to 0. So, when we are taking b not equal to 0, so in that case our expression will reduce to sin omega L by c equal to 0. So, we have sin omega L by c or omega by c L equal to 0. This implies that sin omega L by c equal to sin n pi. So, this is equal to sin n pi. So, n equal to 1, 2, 3. So, you can put different value of n. So, n equal to, you can put 1, 2 and other values. So, n equal to 1 correspond to the fundamental mode, n equal to 2 correspond to the second mode and n equal to 3 higher modes, n equal to 3 third mode, and similarly n. So, you can go up to n number of mode or infinity number of modes. So, this shaft or this shaft will have infinity number of infinity number of frequencies, and so in this case you can write this omega L by C equal to n pi, or this omega you can write equal to n pi by L into C. So, where C equal to n pi by L into root over G by rho. So, this is the expression for omega. So, you can observe that. So, in this case you can observe that the nth frequency is n times of the fundamental frequency of the system. So, in case of torsional vibration of this fixed rod, the nth vibration will be n times the fast mode vibration. So, the corresponding mode shapes you can write the phi x will be equal to or phi n x equal to b n sin omega by c. So, you can write for this omega by c equal to n pi. So, omega by c equal to n pi by L. So, this is n pi by L into x. So, this is the mode shape of the system, and this is the frequency equation or the expression for the frequency of the torsional vibration of the fixed rod. So, the general expression or the general vibration will be general vibration or general theta xt I can write in this form. So, theta xt as it contains n modes. So, I can write this is equal to summation of I equal to 1 to infinity. So, product of, so this will be phi n or phi I x I can write phi I x into q I t. So, here I can write this equal to, so this will be equal to I equal to 1 to infinity. So, this is already I got this equal to b I sin I pi x by L. So, for ith mode I can write this is equal to b I sin I pi x by L, and for q I t I can write this as, so any two functions, this will be a function of sine and cosine term. So, I can write this as C1 I cos omega t plus C2 I sin omega t. So, now you observe that this constant can be multiplied with these two constant, and this equation can be reduced or can be written in this form. So, you can write this is equal to I equal to 1 to infinity. So, I can write this as using some general constants. Let I am writing this is in terms of C or in terms of alpha and beta. So, I can write this is equal to alpha I cos omega t plus I can write this as beta I sin omega t into sin I pi x by L. So, this is the general expression for this free vibration of this rod. So, here this alpha I and beta I, alpha I will be equal to b I into C1 I and beta I equal to b I into C2 I. So, these two constants can be obtained from the initial conditions. So, later in today's class we will see the initial value problem. So, how to find these initial conditions we will find. So, you just observe that this b I for a different mode, this b I will be different. So, you will have a, for n mode you will have n number of constants b1, b2, bn. So, like in case of multi degree of freedom systems also, here you can normalize this and you can find the normalized value for this. So, this normalized value, to find this normalized value you can apply this orthogonality principle. So, to apply orthogonality principle already you know. So, the orthogonality principle can be applied in this way. So, phi So you can write this as phi I x into, so you can multiply with this mass matrix of this. So phi I into I, that is this moment of inertia of the system, into phi I. So this is phi I transpose into phi I x dx. So you make it equal to 1. So if you make it equal to 1, this integral, so in that case you will find the value for this Bn. So for ith mode you can make it equal to 1 and find the constant B. So in this way, by using this orthogonality principle, you can find this constant B, and you may use that thing for finding the response of the system. So let us consider the other system. So in this case we will consider, so let us make the system slightly more complex, that is, let us consider a rod with an teeth inertia. So in this case, if I am adding this inertia to this end of this system, then I have to find the frequency equation for the system. So this case can be used as a practical example. You can consider a well. So from this oil well, you have to use this drill bit or a tool to, so this is the drill and this is the pipe attached to the drill. So in this case it will, so we have to find the natural vibration of this system. So to find this thing, so in this case the boundary conditions will be, so as it is fixed at one end, so this is the rod or the pipe, so it is fixed at the upper end, and in the lower end you are attaching one mass or cutter. So in that case, so you can consider this top end, there is no vibration to the top end, or the rotation is 0 at this top, and and at this end this load will be equal to the inertia load of the system. As you are adding a or attaching a inertia at this end, so the load will be equal to the inertia load at this end. So in this case you can find the equation motion in this way. So you can write the boundary conditions theta. So I can take this is equal to 0. So theta 0 equal to, so one boundary condition will be theta 0 t equal to 0, and the other boundary conditions you can write equal to, so as it is added to the right end, already I told you about these boundary conditions. So in this boundary condition it will be equal to, so this minus j0 del square theta by del t square at x equal to L. So this will be equal to, at x equal to L will be equal to this inertia force. So this will be equal to j0 omega square theta at x equal to L. So this is the inertia force. So inertia equal to j theta double dot, as we are assuming this theta to be harmonic. So I can write this equal to j0 omega square theta. So this inertia force j0 omega square theta at x equal to L will be equal to this minus j0 del square theta by del t square. So that is the torque. So I can write, so this inertia force equal to G, so this will be equal to G I P del theta by del x at x equal to L. So this inertia load will be equal to the load at this end. So this will be equal to, so I can equate this bound at this boundary, I can equate these two terms to find the solution of the system, or to find the mode shapes of the system. So in this case now I can put phi x equal to, already I have written this phi x. So phi x equal to, I can put it as a sin omega by c x plus b sin omega by c x. So, by substituting this theta equal to 0, so this A becomes, substituting theta equal to 0, so this A sin, so this term goes, and so this will be, let me write it correctly. So, this is A sin omega by Cx plus B cos omega by Cx, this is the general expression. So, in this case when theta equal to 0, so this B into 1 will be equal to 0. So, theta equal to 0 implies phi x or phi 0 equal to 0. So, it implies B equal to 0. So, now as B equal to 0, we are left with this term phi x equal to A sin omega by Cx. So, phi x equal to A sin omega by Cx. So, in this expression let us substitute G I p into del theta by del x, del theta by del x. So, this is del theta by del x is the strain, and multiplied by this is the stress, and by multiplying this we are finding this load of the system. So, this will be equal to this inertia torque. So, this is the torque applied. So, this is equal to inertia. So, this is equal to J0 omega square theta at x equal to L. So, this is x equal to L. So, by substituting this thing in this equation, so let us find this is del theta by del x. So, del theta by del x as del phi. So, this will be del phi, and this is also phi, as q is same. So, you can have this is equal to phi, and from this by differentiating this equation, so del phi by del x will give you A cos A omega by c into cos omega by c x. So, I can write this G I p A omega by c. So, this is A omega by c, A omega by c into cos omega by c x. So, this will be equal to, for x equal to L I can substitute this equal to L. So, this will be equal to J0 omega square. So, for phi x I can write this as A sin omega by c x, x equal to L. So, in this case A will get cancelled. So, I can have this expression. So, I can write this thing, this expression in this way, this substituting this G I p omega by c cos omega by c L equal to J0 omega square sin omega by c L. So, or I can write this as tan the sin omega by c L by this cos omega by c L. So, I can write this as cos or tan omega by c L equal to, so this will be equal to J0 omega square, J0 omega square by G I p omega by c. So, this will give rise to J0 omega G I p. So, this is c, and also you know, so this is tan. So, I can write this as tan omega. So, this is tan omega by c L equal to, so from this I can write J0 omega, this expression J0 omega c by G I p. So, I can substitute this value of c, where c equal to root over g by rho. So, I can substitute that thing and I can find this expression. So, this expression will give me, so that is J0. So, this is J0 into, for the c I can substitute it equal to root over g by rho. So, this is g by rho and this is g I p. So, in this way you can find this expression, and this expression you can solve for a practical problem. You can solve this expression to find the frequency equation and corresponding mode shape. So, here J0 is the inertia of the moment of inertia of the rod, G is the rigidity modulus, IP is the inertia of the attached mass, and this omega is the frequency. So, from this expression you can find this omega by C equal to tan inverse this right side term, and you can find this frequency of the system. So, there is a omega term here also. So, J0 omega root over this. Okay. So, in this way you can find the frequency equation. So, from the frequency equation you can find the mode shape of the system. So, let us take the third example. So, in this third example, let me take or let me put two masses or two inertia at this end of the rod. So, for example, this is the shaft is connected to one side to the generator and other side to a motor or a pump. So, if the shaft is connected to this generator and a pump, so due to their inertia, so we have to find what is the torsional vibration in this shaft. So, in this case, let me take it equal to, so I have two inertia. So, one, let me write it is J1 and this is J2, and due to this I can write the general expression theta xt equal to, so this theta xt general expression you can write as phi x into qt, phi x into qt, and here your equation you can write in this form. So, theta xt, let me write this theta xt in this form. For phi x I will write it equal to sin omega by c into x plus b cos omega by c into x, this multiplied by the time modulation. So, this time modulation equal to c1 sin omega t plus c2 cos omega t. So, in this case the boundary conditions will be, so at both the ends you have inertia attached. So, you can write the boundary condition like this. So, at x equal to 0, so you can have J1 d del square theta by del t square, this is the inertia torque. So, this will be equal to, so for the left end it will be equal to G I1, so it will be equal to G, so I can write this is equal to IP. So, this is the polar moment of inertia of the shaft into del theta by del x, and for the right end at x equal to L I can write this as J2 del square theta by del t square equal to minus G IP into del theta by del x. So, already you, so this expression came from this expression, already you know this T by J equal to T by J, I can take this as IP. So, T by J as G theta by L. So, from this you know this torque. So, this torque will be equal to G IP, and for small rotation, so this will be equal to, so this torque will be equal to G IP into del theta by del x. So, this is general expression, you know this is G by G theta by L. So, this is the general expression for torsional vibration of a shaft. So, the torque at this end can be represented by this. So, this will be G IP del theta by del x. So, for small strain, so del theta by del x. So, this torque will be equal to the inertia torque at these two ends. So, at this left end the inertia torque will be equal to G IP del theta by del x, and at the right end it will be equal to minus G IP into del theta by del x. So, in this way, so after getting these boundary conditions, so you can substitute this thing in this generalized mode shape, that is theta xt or theta xt equal to a sin omega by Cx plus b cos omega by Cx into this time modulation, that is C1 into sin omega t plus C2 into cos omega t. So, by substituting that thing, so you can write, so if you differentiate it twice and write, so the expression will becomes like this. So, you can write at substituting for the left end, you can write, so j into a sin omega by c x plus b cos omega by c x into, so as you are differentiating it twice with respect to time, so it will be minus c1 omega square cos omega t, and then it is minus c2 omega square sin omega t. So, this is the left side, that is j1 into, so this is j1 into del square theta by del t square. So, this will be equal to g I p. So, this is equal to g I p into del theta by del x. So, if you differentiate it 1, so this becomes a omega by c cos omega by c x minus b omega by c into sin omega by c x. So, this into, so del theta by del x you are finding. So, you have differentiated that, and this into it becomes c1 sin omega t plus c2 cos omega t. So, just you have differentiated with respect to x. So, this is the term you are getting del theta by del x, and as you have not differentiated with respect to t, so this is this q t term remains same. So, you can note that this term becomes, so this is equal to, this term is equal to minus omega square into this term. So, you can cancel it out. So, you can write this expression in this way. So, this expression by after cancelling you can write, so and by substituting theta x equal to 0. So, when you substitute x equal to 0, this sin term will go, and here also the sin term will not be there. So, the expression, so from this you can write this expression equal to j1 b omega square plus g I p a omega by c equal to 0. So, this is one expression you are getting from the left end boundary conditions. Similarly, from the right end boundary condition, so by substituting that thing you can write in this way. So, j2 omega square into a sin omega by c x, when you are finding j2 del square theta by del t square. So, you differentiate that theta twice with respect to time, that means you have to differentiate the time modulation term, that is q t twice, and keeping this phi x constant. So, a sin omega by c x plus b cos omega by c x into, so by differentiating it twice you have taken this minus omega square common. So, the remaining term, so it will becomes q t I can write. So, the expression for q t you can write here. So, this will be equal to minus, so you just note that here you have a minus sign. So, this is equal to minus g I p del theta by del x. So, del theta by del x, for that I can write this is equal to, so when we are differentiating with respect to x, so this omega by c term you can take it out. So, then it becomes a cos omega by c x minus b sin omega by c x into, similarly that q t term will be there. So, this q t term you can cancel. So, now you can substitute x equal to L. So, if you substitute x equal to L, this equation or this equation you can write as minus, you can write this equation as minus j2 omega square sin omega by c L by omega by c g I p minus j omega square sin omega by c L plus omega by c g I p cos omega by c L into a. So, I am collecting the terms with coefficient a and b. So, here you have this term and here this term. So, I am collecting the coefficients of this. So, I will write this minus this equal to 0 after substituting x equal to L. So, from that I can write this expression. So, this equal to or this plus minus j2 omega square cos omega by C L minus omega by C g I p sin omega by C L to B. So, you have two equations. So, in the first equation you can write, you have written this thing g I p omega by C into A plus g 1 omega square B, this is equal to 0, and in the second expression you have this minus j omega square sin omega by C. So, this is equal to 0. So, I can take a negative sign common. So, I can write, so this positive, so I can write this positive and this minus and this term as positive. By taking a negative sign common, I can write this expression in this way. So, I have two expressions, so with unknowns A. So, I can write this matrix in matrix form, I can write this expression. So, I can write this in this way. So, it will be g I p omega by C, then j2 omega square sin omega by C L minus omega by C g I p cos omega by C L, and in the second column it will be j1 omega square and this is j2 omega square cos omega by C L plus omega by C g I p sin omega by C L. So, this into A B. So, this is equal to 0 0. So, from this expression you can find or you can see that this for non-trivial solution. So, for non-trivial solution, that is when both A and B are not equal to 0, the determinant of this matrix will be equal to 0. So, you can find the determinant of this matrix. So, the determinant will be these multiplied, that is A11. So, you can multiply this first column with this A11 into A22 minus A12 into A21. So, you can make it equal to 0. So, this way you can find the determinant of the system. So, by finding the determinant of the system, you can write the final expression for this case in this way. So, the final expression will be omega square into cos omega L by C minus omega C j1 g I p sin omega L by C into j2 plus omega g I p by C into sin omega L by C plus omega C j1 by g I p cos omega L by C. So, this is equal to 0. So, this is the frequency equation you are getting for this system. So, you can note from this equation that for 1 omega value equal to 0. So, omega equal to 0 correspond to the rigid body motion of the system. So, if you have a rod, so in this rod, if in the both ends you have two masses or two inertia are attached, let one side you have this flywheel, other side you have some other inertia mass you have attached. So, in that case it may have a free motion like this. So, the body can move up and down. So, this is the rigid body motion of the system. So, in this case of the rigid body motion, so omega equal to 0, as there is no vibration of the system, but there is only pure displacement, that is the displacement equal to 0, omega equal to 0, the whole system will move simultaneously. So, there will be no relative motion between any particle of this body. So, this is the rigid body motion in this case. So, when omega equal to 0, so the system will have a rigid body motion and or the system. So, in this case the whole system will rotate without, so the whole system will freely rotate. So, in this case of torsional vibration, the whole system will freely rotate and you will have this omega equal to 0. So, the other frequency you can find from this by solving this equation after substituting this numerical value of different parameters. So, in this way you can derive the frequency equation of the system. So, after deriving this frequency equation of the system, now you can write from this matrix A in terms of B. So, after getting this A in terms of B, you can substitute that expression in expression for phi x. So, the final expression will contain A into some function x. So, by normalizing, so you can find this A value and you can write the expression for different modes in the normalized way. So, in this way you can find the torsional or mode shapes of the torsional vibration of this torsional system. So, in this case I have studied, I told 3 different systems. One case both end are fixed, in other case one end is fixed and other end contains a mass or inertia, and in the third case both end contain inertia terms. So, in these 3 cases you have seen only in case of the only in the first case, that is fixed. So, you have a expression or you have a closed form solution for this system, or you can manually you can determine this solution of the system, but in other 2 cases you have to do this computational or you have to take the help of numerical analysis to find the solution of these systems or find the solution for these frequency equations of the system. So, after finding the frequency equation you can find the mode shapes and normalized mode shapes of the system. So, let me briefly tell you about this natural vibration of the system, natural vibration of the continuous system. So, in case of this continuous system, so already you know that the vibration can be written as, or the free vibration can be written as the summation of all the modal vibrations, or you can write this u x t, that is if u is the displacement at any time at any position x. So, this thing you know that you can write it in this form. So, you can write it in this form I equal to or n equal to 1 to infinity. So, a n sin omega n t plus b n sin omega n t into, so this into you can write. So, this is the time modulation and you can use this mode shape. So, the mode shape you can use in this form. Let the mode shape, let me write. So, this is equal to, I can write it as C1 cos omega by C x plus C2 cos omega by C into x. So, this way you can write the generalized solution of the system. So, let for example you take the case of a simply supported beam. So, in case of the simply supported beam you can write the displacement, transverse displacement W x t in this way. So, you have written this thing as a 1 n cos omega n t plus a 2 n sin omega n t. So, this into the mode shape. So, in this case of simply supported beam, the mode shape has reduced to the form of sin n pi x by L. So, this thing you can write sin n pi x by L. So, this is the transverse vibration for a simply supported beam. So, in this case, so the total free vibration is expressed as the summation of all modes vibrations. So, if a particular mode is dominant, you can tell that the resulting vibration will be that of that particular mode, otherwise it will be the summation of the all modal frequencies. So, let us consider the initial condition in this way. So, I can consider the initial condition Wx0, let at a particular time this Wx0 equal to A sin n0 pi x by L. So, that means at a particular time let the beam is vibrating with a particular mode, or the initially the beam is vibrating with a particular mode, that is the at t equal to 0, let us consider that the beam is vibrating with the second mode. So, this is the mode shape of the second mode. Already you know the mode shapes of the first mode can be given in this way. So, this is the first mode, this is the expression for second mode. Similarly, third and fourth mode you know. So, let for a particular mode, that is n0, so the beam is vibrating at t equal to 0 with this mode, and there is the slope is 0, this that means dw by dt at t equal to 0. So, that is the velocity. Let us consider it has a velocity 0, and at beginning it vibrates with a particular mode, or it is vibrating with n0 mode. So, now substituting these two initial condition in this expression, we can find this A1n and A2n, and from that we can find or we can obtain this general solution of the system. So, this is the initial value problems. So, this is the natural vibration of the system can be considered from this initial value problem. So, in this particular case, so now substituting this Wx0 equal to A sin n0 pi x by L. So, I can write this as summation. So, this summation, so this is n equal to, I can put it n equal to 0 to infinity. So, n equal to 0 to infinity I can take. So, this will be equal to A 1 n sin n pi x by L. So, at x equal to 0, so let me first write this expression. So, A 1 n sin n pi x by L will be equal to A sin n pi x by L. So, I can write this other expression as omega into alpha 2 n sin n pi x by L equal to 0. So, from the second expression, from the second, by differentiating this and substituting this x equal to, so for any value of x we are finding, so we are substituting at t equal to 0, the initial condition t equal to 0 if you substitute in this case. So, Wx0 equal to A sin n pi x by L. So, substituting t equal to 0, so this expression sin A2n becomes 0. So, this becomes A1n only. So, this is summation A1n. So, here you have sin n pi x by L. So, this is the initial condition, that is A sin n0 pi x by L. Similarly, differentiating this expression, I can write dw by dt at t equal to 0. So, then differentiating it once, so you have this cos will become sin, and so this A1n term will go A1n into 0. So, this becomes A2n. So, this as it is cos, so it will becomes 1. So, A2n, so this is A2n. So, let me write A2n sin n pi x by L. So, this is sin n pi x by L equal to 0. So, this is your expression, let it is equation 1, this is 2, and now this is 3 equation. So, from this expression you can see that this equation will be valid. Let us consider this first expression. So, these equations will be valid only if and only if. So, this n will be equal to n0, because sin n pi x by L in the left hand side you have, and in the right side you have, this is sin n0 pi x by L. So, this equation will be valid only if this n equal to n0 and this alpha or A1n equal to, so this n equal to n0 and this A1n will be equal to 0 for n not equal to n0, that is those terms will not be there, and equal to a for n equal to n0. So, for n equal to n0 this a1n should be equal to a, and for other time this term should vanish, otherwise this left side will not be equal to right side. So, in this case I can write this expression also, this a2n, from this a2n will be equal to 0, a2n equal to 0 and a1n equal to, so you obtain a1n equal to 0 for n not equal to n0 and equal to a for n equal to n0. So, by substituting these things, so you can write this w, so this is w is the displacement, so this w xt, w is the transverse displacement, w xt equal to a cos omega n0 t into sin n0 pi x by L. So, you just see that the resulting vibration in this case. So, if you have started with a particular mode, that is you have started with n0 mode of the system, then the resulting vibration will be in this form, that is a cos omega n0 t into sin n0 pi x by L. So, when we are starting with a particular mode or the initial condition is such that it is vibrating with a near a particular mode, then that mode will be dominant and other modes will be not so dominant. So, the resulting vibration will contain that mode, and similarly you can find for other cases. For example, so you can take this as an exercise problem and you can do. So, for this taut string, so let us take a string, and in this case let initially you have, so this is the string in tension, initially you have take it up and then left. So, when you take it up, so this side I can take this equation in as, so this is your x direction, this is the y. So, I can write this y x0. So, the initial condition for the string I can write in this form. So, y x0 equal to, I can write this as, let it is 2a. So, this position, let this position is, so this is 0, this is L. So, this is a 2a x by L, let me put. So, this is for t for 0 less than equal to x less than equal to L by 2. So, this is L by 2. So, for L by 2 this equation is 2a x by L, and for this half the equation is, so you can write this expression for this equation, that is equal to 2a 1 minus x by L. So, this is for L by 2 less than equal to x less than equal to 1. So, in this case you can see, so with this initial condition you have to find what is the resulting vibration of this string. So, by taking these two, so this is the expression for this displacement. So, you require another initial condition also, let the velocity, that is del y by del t at t equal to 0 equal to 0. So, let you have given one initial velocity and no initial displacement to the string and left. So, at t equal to 0, velocity equal to 0. So, with this you can find the solution of this system. So, to start with, you just take the expression for general expression for the string vibration, that is y xt equal to phi x into q. So, summation of n equal to 1 0 to infinity. So, you just take in that same way. So, that is equal to a n. So, you can write this expression in this form, this is equal to a 1 n. So, let me write in that way, a 1 n cos omega n t plus a to n sin omega n t. So, into, so in this case also if it is fixed at both the ends, then you can take this is equal to sin n pi x by L, sin n pi x by L. Already you have seen for the fixed string or the string fixed at both the ends. So, you can write this expression in this way. So, now applying these boundary conditions. So, before applying these boundary conditions, you can write this in the terms applying this Fourier series. You can write this expression, and to apply this Fourier series, you can, from the Fourier series you can find that this will be equal to a n will be equal to 0 and the b n terms of that expression. So, this expression you can write it as summation a n cos omega n t plus b n sin omega n t. So, you can express this y x t in terms of harmonic function, and so in this case this is omega n x, this is omega n x, a n sin omega n x plus b n sin omega n x. So, after writing this in terms of the harmonic function, so you can find that for this particular case a n equal to 0 and b n equal to minus 1 to the power n minus 1 by 2 into 8 a by pi square n square, and this b 0 equal to 0. So, now by taking these initial conditions, so you can see that this a 2 n equal to 0, and from the other condition you will get, that is n equal to 1 to infinity a 1 n sin n pi x by L equal to summation n equal to 1 to infinity b n sin n pi x by L. So, this similar to the previous case, this equation will be true if and only if this alpha, this a 1 n equal to b n. So, when this a 1 n equal to b n, so this expression will be true. So, in that case you can write this expression w x t. So, w x t, this is the displacement. So, this displacement relation you can write in this form. So, w x t equal to n equal to 1 to infinity minus 1 n minus 1 by 2 into 8 a pi square n square pi square cos omega n t sin n pi x by L. So, in this way you can find the free vibration response of this continuous system by applying these initial value or initial conditions. So, in this way you can study the free vibration response of the continuous system.